First of all, I talk about the motivation that the why the reheating phase is important. Then I'm talking about the non-gravitational coupling. So we took different coupling between the inflaton and the daughter field sector, and we'll see the where the gravitational interaction lies in the rest. And then talking about the dark matter phenomenology in terms of FIMPs and WIMPs. First of all, the why the observation, there are some observation challenges in the early universe, because our knowledge of this cosmic history of the universe is based on the two major observations. One is the cosmic microwave background, and another is the BBN. Typically, the CMB is provided accelerated expansion during the early phase, which is the inflationary phase. And typically, the energy scale is around 10 to the power 15 or 16 GeV, and the duration is around 10 to the power 36 seconds. And whereas the BBN actually predicts the quantities such as the light element and the energy scale around 1 eV, and the time scale 1 second. So the problem is that there is a massive gap in terms of energy and the time scale between the CMB and the between the inflation and the BBN, and which is basically the poorly understood from both theory and the observation. So here the Reheating dynamics basically lies. So after the end of the inflation, the universe is cold dark and dominated by the inflaton field. Now the problem is that how this inflaton dominated universe changes to a radiation dominated state, which is basically need for the Big Bang nucleus. And here the Reheating dynamics light or the inflaton field is down to the minimum of the potential, and when it oscillates, it can couple with the other daughter fields and it can produce entropy, giant entropy. And this is a schematic diagram of the evolution of the moving Havel scale, and we can see if we introduce the Reheating phase intermediate between the inflation and radiation, it can influence the expansion history, and that actually also modified your NSR prediction due to this extra Reheating. Because now you have to entropy conserve from the TRE to D0, and that actually constant your NK plus NRE, not only. This is a typically Reheating scenario we consider. So we consider the possible interaction between the inflaton and the radiation field. So we took 3 non-gravitational coupling, phi square, and this is the Fermionic one. And here this is the gravitational coupling. Gravitational interaction is always present. So the exchange of graviton from inflaton scattering the standard model particle. And this is the corresponding the decay channel for each processes. And we also took the effect of the Bose-Einstein and the Pauli blocking effect here there. So it can enhance your production rate, or it can also reduce the production rate for the case of the Pauli in case of the Fermionic. And this is the decay which corresponds to the gravitational. So now go to the Reheating setup. Here, this is the Boltzmann's equation, and the first equation is for the inflaton energy density, and we took both the non-gravitational and the gravitational coupling into that. And this is for the radiation energy density coming from the non-gravitational coupling one, and this is for the gravitational one. And we took the analysis here. And in terms of calculating the inflaton equation of state, we basically average over 1 oscillations and use a virial theorem. We can relate the omega phi, W phi with the exponent of the potential in the n minus 1 there. And the initial condition is coming from that at the end of the inflation, the total parameter epsilon is 1, then we can relate the rho phi with the potential value at the end of the inflation. And rho r is typically 0. This is the initial condition for the Reheating. Now go to the how we define this Reheating temperature. So Reheating temperature is defined at the point when your inflaton energy density and the radiation energy density are equal. So after that point, actually radiation domination starts. And the Reheating temperature we can relate from the Stephens-Boltzmann equation from the radiation energy density to this relation. And there is typically another assumption, and another is that the co-moving entropy density is conserved from the Reheating point to the present day, as we consider all the particular produced at the time of Reheating. So this is the entropy conservation. And here for a particular NA, we can fix what will be the NK value, because the NK plus NRE now is for a particular Reheating temperature. And now there is the restriction we have that we have to end the Reheating at the before BBN. So it's typical we took the Reheating temperatures greater than 10 eV. And there is another upper limit is coming from tensor to scalar ratio. The recent biocapture suggests that the tensor to scalar ratio is much greater than 0.036, and from there we can estimate the inflation energy around 5 into 10 to the 13. So now go to the Reheating setup. I only talk about here the bosonic Reheating, and here we also consider the two types of phi 2ss and phi 5s decay channel. And we have the 3 different cases. In the first cases, when your coupling is greater than some critical one coupling, then your entire Reheating dynamics will be dominated by this non-gravitational coupling. And now when you have some intermediate coupling between G1 to G2 critical, then you have the some portion is dominated by the gravitational one, but at the end of the Reheating is always dominated by the non-gravitational one. And in the third case, there is coupling is less than your critical 2. And in that case, you have the gravitational channel is always dominating, but there is a, you have to, your equation of state greater than 0.65. Otherwise, there is no gravitation. And this is the evolution. For GI greater than GCI critical, you can see that this is the evolution of the inflaton, the black one, and the green one. These two are for without thermal effect, with thermal effect, and we choose coupling such a way that we get a safe temperature. And you can see the with thermal effect, this term is dominated by your the Bose enhancement regime. This one, there is an increasing factor, and these blue one is for the gravitational contribution. And you can see always your whole dynamics is dominated by your non-gravitational coupling, and we get reheating around here. It's around 10 to the power 12. And now they are in the second case where in the middle panel we choose the coupling in the intermediate 2, and we can see that initially it is dominated by the gravitational one, and then finally it takes part the non-gravitational coupling part, and reheating happen. And in the third case, always your gravitational channel is down. And this is the for bosonic and Fermi rating how your temperature varies with the scale factor. This is the when your thermal effect is in active mode, when the radiation temperature is greater than m5t, and here is a radiation temperature less than m5t, and how your temperature evolves. It's a scale factor, normalized scale factor. Now there is a variation of the dimensionless bosonic coupling with respect to different omega phi, and here we can see different regimes. In the first, this magenta color, there is this portion is entirely dominated by your that particular direct decay channel, and this yellow region, the some portion is dominating by your gravitational one, and some part is dominated by your direct decay. But finally, your reheating temperature is determined by your direct decay channel, and this one is dominated by the gravitational interaction. And this is the same for 552SS process. Okay. Now go to the dark matter sector, where we consider the dark matter production from both inflaton and from the radiation, and we also took from the infrared scattering through the exchange of graviton, and and also considered the dark matter production from the radiation bath. But here we took some effective vortex, and so yeah, the sigma v is some free parameter, the constant parameter, free parameter. I will only discuss the dark matter production from the radiation channel here. So this is the Bose-Bonds equation for the dark matter number density. You can see the first contribution from coming from the radiation bath, and this is the gravitational contribution from the inflaton, and this is from the radiation bath to the exchange of. This is the equilibrium number density have. So I only talk about these two scenarios of FIMP and WIMP. When the cross section is too much small, then dark matter never reach the thermal equilibrium. You always Nx is very less than Nx equilibrium. So this is the FIMP kind of scenario, and the WIMP scenario you have the larger cross section and dark matter can reach the thermal equilibrium, and it's possible that a freeze out happened during reheating. So here is when the freeze out happened during reheating. If your mass scale, the mass is greater than 3 TRE, then there's a possible that your freeze out happened during reheating, and this is yield the dark matter number density over the entropy density. If we see the after freeze out point to reheating, there is a non-trivial dynamics here, and that can imprint in your sigma v mass plane. Similarly, for the Fermi reheating, you can see the same kind of scenario that, and this is coming from your temperature evolution, because here the S is playing the role, because now T is not proportional to 1 over A, so this dynamics is in the dark matter evolution. And this is your abundance plot. You can see that if we see the dark matter parameters here, so you can see that the lower part is from the FIMP scenario, and the upper part is for the WIMP one. And we can see that if dark matter produced during radiation domination, you always have some constant cross section. It is around 10 to the power minus 9 to 10. But when it freeze out happened during reheating, so your sigma p is much lower. And somehow we are able to manage to get it off from the observation, indirect observation. So let's talk about the main points and outcomes. So for the purely gravitation reheating, sets a lower bound of the reheating temperature, and also sets the lower limit on the direct coupling parameter, above which we have the coupling domination. And the thermal correction in the production rate, significantly modified production rate. And we can see that the reheating temperature can be the maximum temperature. So the initial temperature is not the maximum one, the reheating temperature can be maximum. And the another thing is that in the dark matter sector, we always see there exists a maximum dark matter mass above which we are not able to go. Then always we have the under abundance. And that is strictly depends on the temperature and the inflaton.
Thank you very much. Finishing time. No wonder I was expecting a question from you.
Hi, Riajul. Thanks for the nice talk. So basically, in the bosonic reheating, you have taken your decay product to be massless.
Yeah.
So any comment what would happen if your decay products are massive?
That's possible. The dark matter can be produced from that decay. We can also
But
consider in that paper.
yes, but in that case, if you consider non-zero omega, so your perturbative reheating gets blocked after some like if your n you have taken 5 to the 5, your potential as 5 over 2n.
Yeah.
So for n greater than 1, your perturbative decay is blocked. So any comment what would happen if you have you take massive
Oh, you are talking about if we take the massive particle.
massive decay product. Your
Dark matter domination start without.
so the decay is no longer available. Like perturbative decay is no longer available. So what would happen that like?
Why perturbative decay is not available for the massive particle?
That you can take like this. If you have taken those decay products to be massive.
Inflaton particle can decay massless also the massive one.
But for n greater than 1 is not possible. Perturbative, then you have to consider non-perturbative decay. Okay, nice.
Okay, so any comments? Okay, so one thing, so can you just quickly explain why omega has to be greater than 0.6 for this gravitational reheating to be effective? What is going on?
You can see the gravitational decay channel is 1 over mp to the power 4 subspace. So now problem is that all the production happened during that initial stage. And now if your inflaton is dilutes faster than your radiation, so like your greater than 1/3, so whatever radiation produced at the initial time, now your inflaton dilutes faster than your radiation. So somehow you are able to manage radiation domination without H is equal to gamma crossover.
No, but your final slide, you have shown that gravity for the parameter space where gravitational reheating dominates over the other requires W to be
greater than 0.65. Yeah.
Where from that is coming? I mean,
from the BBN, because from when your omega phi greater than 1/3, then your inflaton dilutes faster than radiation, but still you are getting temperature lower than BBN. But as we increase your omega 5,
no. My question is that why gravitational reheating is dominating over the standard part of it?
Oh, because your coupling are too much small. Because there is a coupling on there is a restriction on the coupling. One second. If your coupling is less than that, only then gravitational reheating dominates. Otherwise, there is always.
But then why? So coupling is small from left red corner to the green right corner. But why W phi has to be greater than 0.6 to gravitational reheating?
Okay. So first, if you only consider the gravitational interaction without taking any non-gravitational coupling, then we can see that from 0.65, you start to get the reheating temperature above BBN. Okay. Now we increase the 0.65 to n/1 kination, and you get temperature from BBN to 10 to the power 6 GB. Now, whatever coupling you give you 10 to the power 6 GB temperature, that is the subdominant one. That's the case.
Thanks. Yeah. So any more comment questions? So if not, so thanks Riajul once again. So